Hello everyone, welcome to another undergraduate seminar series. Today's speaker is Eduard Plint. He's a third-year applied math student. And the title of his talk is What Happens if we change the Thank you, Eduard.
Hello, everyone. Judging by the room, I'm pretty sure everyone here is fairly comfortable with like vector spaces and specifically inner special cases of inner product spaces. Such
I don't know what that is.
but you even tutored the linear algebra. Anyway, so we're all familiar with, at the very least, the vector spaces that we do in second year with dot product and so forth, and that quite nicely it generalizes into what we call inner product spaces. So a product on a space is a function that takes two elements from that space, combines them in some way, and outputs a real number. So the familiar way of doing an inner product space is we've got an inner product, which is a bilinear form, meaning it's a two-variable function that is linear in each of its components. It's symmetric, so it doesn't matter which order you do the inner product, and it is positive definite, so it's non-zero, or any vector taken product with itself is non-zero unless it is zero. But everyone has seen these before. It's quite ubiquitous with maths in general. So what happens if we change things slightly? So I propose a different form, or I'm very tempted to say product on a space, but that's not quite right. So I'm going to use the word form. I'm going to propose a different form on a space, which I'm going to call omega. So firstly, omega is, again, bilinear, so linear in both of its components. It is skew symmetric, so that means if you swap the order of which you do it, you pick up a minus sign. So the analogy would be cross product, but cross product isn't a bilinear form in this sense. And then it is non-degenerate. So that means if I have a vector and I'm going to take its form with any other vector in that space and it equals zero, that means that vector I've taken must be zero. So I just want to sort of highlight that because it might pitch up a bit later. The inner product displays non-degeneracy in its positive definiteness. And that's sort of a subtle thing that underlies and pops its head up later if we get there in the time. And I just sort of want to highlight the first quirk of this form on a vector space, is that our skew symmetry implies that any vector taken with itself will equal zero. So if you like go on Wikipedia and so forth, this is called a symplectic form, and any vector space equipped with a symplectic form is called a symplectic vector space. If you go to Wikipedia, the version they give is skew symmetry we get skew symmetry with this condition rather than that condition, but you can get between them quite easily. So and then just a disclaimer, I'm doing everything in finite dimensions. I don't feel like dealing with infinite dimensions just yet. Yeah, sorry, Dr. K. So let's start with an example. So let's work in R2, and we're going to define a symplectic form such that we have this. So if you're quick and you've done lots of stuff with matrices and so forth, you will notice that that is essentially the determinant of a 2x2 matrix with U and V being the column vectors. So that's sort of a theme that's going to pitch up in this talk. So it's pretty easy to check that it's a bilinear form because properties of determinants, I suppose I can say properties of determinants, but more specifically, it's pretty easy to show that this expression is bilinear, and it is also quite easy to show that it is skew symmetric just because of properties of determinants. But it's a bit more work to show that it's non-degenerate, so we'll do that first. So let's start with saying, okay, we've got a vector v such that we have that our non-degeneracy condition, so that any other vector taken form with v is equal to zero. So in particular, we can choose u to be 1, 0. So this will give us that 0 is equal to, swap things around. it doesn't matter in this case. We'll have v1 times 0 minus 1 times v2, and so that just gives us that v2 is 0. Okay, cool, that's a start. Now we can take a different u to try out work with. Let's take 0, 1 instead of 1, 0. And then doing a similar calculation to what we did there, we can show that v1 is also 0. So therefore, we have a vector v. We've got our vector v being 0 for non-degeneracy. So therefore, this determinant type looking thing is a symplectic form. So it's quite easy to generalize it up to vector spaces of size R2n. So we can generalize it. Okay. I appreciate the sympathy. In the following way, where we again take this sort of shape. So let's what letters did I use? I use these letters. It's fine. I bounce. Okay, I'll just skip a bunch of stuff, and we get up to where we've got our u being a vector of the form a1, b1, a2, b2, okay, all the way up to an, bn, and our v is all of the STs. So to, again, just highlight how this works, we're just essentially grouping each part of these into a little 2x2 matrix and then taking determinant like that. So I specified 2n. So what happened to all the odd numbers? So I'll just quickly give an example with R3, a possible way of, we'll show properly now that it must be an even power, but I'll quickly do an example with R3 to show that stuff doesn't work, mostly because of S3, the non-degeneracy. So let's consider vectors v1, v and u in R3, where we've got v1, v2, and v3. And one of the things we'll try, or the thing we'll try just for this example, is taking this determinant structure, and instead of extending it in 2x2 blocks, we'll just take that determinant and then take that determinant. Okay? So this gives us omega of VU is V1 U2 minus V2 U1 plus V2 U3 minus U2 V3. Now we can factorize this in terms of U1, U2 and V2, where we get V3 and U2 plus U1 and U3 V2. Okay, so now we want to fix our V such that this thing is equal to 0. So that means we need to show that it works for any U, right? So I'm just going to be very sloppy with notation and just say equals 0 for some V for any U. So in particular, let U equals 1, 1, and 1. Okay? That gives us that V1 is equal to V3, because now this turns into 0, so this part disappears. This is a 1, so we just solve for V1 and V3. So a possible solution for V would be 1, 0, 1. But that's very much not the zero vector. So then here we don't have degenerate, so here we have a degenerate form instead of a non-degenerate form. So at least in the R3 case, we have an example of a form that isn't symplectic. But before I talk, so we'll get to the basis now, but I first want to, do I still need this? I don't think so. So let's me first recall something that we have for inner product spaces, specifically that we can, where G is an inner product, we can write this inner product as in its matrix form, where we take a conjugate, I think the correct term is conjugate with a matrix. Now, this is more than just for inner product. You can show that any bilinear form can be written in this matrix form. So that means we can do it for a symplectic form as well. But the thing is, to do that, you need to do it relative to a certain basis. So let's quickly get a basis for our symplectic vector spaces. So let me quickly write all of this stuff. So now, I feel like I do have the high ground. Wheels would make this far more dangerous than it has to be. Um, um, so we've got a basis in terms of these EF basis vectors, where we've got the following properties on the basis. So first off, for any symplectic form, E1 or EIFI is equal to 0. So for all I up until n, but then the remaining things is all just saying stuff is equal to 0. Let's do this. Sorry, typo. And for all I not equal to j, for all I not equal to j. Have I got this the right way around? Yes. And so it basically says the EF pairs take form to 1, but any other combination of any other basis vector equals 0. So the way you get this is much the same as you would do in an inner product space setting, namely with the Gram-Schmidt process. But there's a crucial first step to establish the fact that you get an EF pair that comes from the non-degeneracy. So I'll just quickly start that off, and then the remains can be done quite easily if you really feel like it. So first we choose a non-zero vector. In V, and we let our E1 equal V. Now, since E1 and V are non-zero, we know from S3 that there exists a W such that E1W is equal to a non-zero constant, right? So now we're going to let our F basis vector be a scaled version of this W. And we can, so therefore, by the bilinearity of the symplectic form, we have that this is equal to 1. And then the remaining stuff can all follow from Gram-Schmidt in each component and so forth. And in particular, I just want to note that the F basis and the E basis vectors are non-parallel. Otherwise, by the bilinearity and non-degeneracy, you would get, oh, is it? Yeah, so by the bilinearity, you'll be able to say E taken form with E will equal to 0, which is obviously a contradiction of which we just showed. So, and then the rest of the properties come from Gram-Schmidt, and in that you can show that in particular the dimension of V is some even number, in particular 2n, with respect to your basis. So that just sort of highlights again how important this non-degeneracy, and if we think back to how we get basis for an inner product space, we use the positive definiteness to show that the bases are linearly independent. So non-degeneracy sort of rears its head again. So the standard basis for a vector space R2n is basically the same as for a Euclidean space in that it's 1 in one component and 0s in the rest, which is quite nice. So now now that we've got that, we can write for the standard symplectic form we wrote earlier, a matrix representation. So if we've got our standard symplectic form on two vectors, we can write in this form where J is the block matrix in terms of J, a smaller 2 by 2 matrix and a bunch of 0 matrices. Where J is, and so this is quite nice. And then I didn't have time to fit it in, but later on you can get, like if we in an inner product space, you get linear isometries, you can get a similar version for this one, and you use this sort of thing in that discussion. And then before we move on to what I think is the interesting bit of the talk, I want to just introduce a couple of notions that just to like show that this works for any really weird stuff you want to think up, as well as if we've got time, something I want to show at the end. So I'm going to do a magic trick for you guys. Bada bing, bada boom. So I'm going to introduce something called the dual of a vector space. So the dual of a vector space is basically the set of all linear transformations from that vector space to R. So let R be a vector space. Now we're going to define a new vector space in terms of R and its dual, namely the direct product or direct sum between these. So what we're doing here, we're saying here's a new, I'm assuming it's a vector space, but you can show it's a vector space. But here is a new vector space of, we take an element from R, we take elements from its dual, and those two things together next to each other are now a new vector in this new vector space. And now we'll have a form from V to R where we define it as Sx minus Ty. So again, same determinant-like structure, but now we're doing it with a vector and a linear transformation acting on that vector. So it's quite flexible in how you can generalize and move around with these things. So that's just a quick example that's not really going to come up later, then yeah, so like I said, I'm going to take our attention back to the skew symmetry that sort of says any vector taken form with itself is equal to 0. That causes problems because that means in a symplectic vector space, we can't really have a notion of the length of a vector, which is kind of a nice feature we have with the inner product spaces. We can define the length of a vector. But so we can't do that in a symplectic vector space. But we can still talk about orthogonality in a vector space. And it does some kind of weird stuff. So we're going to define orthogonality in the same way as in any way. Two vectors are skew orthogonal or omega orthogonal to each other if their form is equal to 0. Pretty standard. So we're going to define our, for a given set in a vector space, the orthogonal complement of that set is all V, we just say all U, such that for all V in S, the form taken between those two is equal to 0. So we've got this definition now, we've got sort of what's going on. Let's do a little example to see what's going. We'll go visit R2 again. So let's visit R2 and talk about a vector, just an arbitrary vector like this. So it's pretty easy to see that, and then we just let S be this set. So it's pretty easy to see that the orthogonal complement of S, and this is with respect to the standard form we had earlier, it's pretty easy to see that it's just all of the scalar multiples of said vector. Because we can use the bilinearity of the symplectic form to pull out any scalar multiples, and then the vector scalar formed with itself equals 0. So the way this looks is if we've got our vector v here, that means that we've got that is the orthogonal complement. So the vector generating the orthogonal complement of its vector space is itself in that space. So if I just let U equals to the span of S, we have that U is equal to its orthogonal complement. Which, I don't know, feels a bit weird, especially when we're used to orthogonality meaning pointing in completely different directions. This is sort of contrasted with the R2 case with the normal normal orthogonal complement. Okay, so we've got this interesting behavior. Let's see what happens if we, like, I don't know, push it up a dimension or 2 or 3 in this case, and give specific numbers just to see what stuff happens again. So now we're going to work in R4, and in particular, we're going to let our V be 1, 2, 3, 4. Okay, so that means our orthogonal complement of S is all of the vectors, or all of the vectors like so, where, I hope I don't run out of space. So that means I'm just going to do that. So let's see how quickly I can calculate determinants. Yeah, okay, cool. Right? Do I have the minus signs the wrong way around? I do. Unless I did it wrong in my notes. It doesn't matter. It's fine. It's up to I can just multiply by a minus sign. So doing the standard exercise, if like you were trying to, if you've got a, whatchamacallit, words are hard. What's that? What's when you're trying to find the solution space of a singular matrix? That those words. So we just plug in variables and solve for one of them to get and then t comma u for s, t, u, and r. So we've got this orthogonal complement, and then we can decompose it as follows. So we can write this orthogonal complement as the span of the following three vectors. Uh, okay, cool. But again, there's a bit of weirdness going on, which is our vector v is a linear combination of these three vectors. Not, I can't remember the exact linear combination, but those three are linear combination of each other. So what we get is, if I just use the same notation here, is that U is a subset of its orthogonal complement, which it's a bit unexpected, don't you think? Okay, so let's just put a pause on this. We can think about this later. Let's carry on forging ahead. So despite this funkiness with orthogonal complement, orthogonal complements and so forth, we still have a pretty nice result that I think most people would be quite familiar with from linear algebra, is that we still have rank nullity theorem in a symplectic vector space, which, I don't know, considering we're used to orthogonal complements being disjoint from each other, I found it surprising when I first saw it. So in particular, if we've got a vector space V with subspace U, the dimension of U plus the dimension of U omega is equal to the dimension of V. And fun fact, this is a special case of, for those of you who, I think almost everyone here has done at least some algebra, abstract algebra. This is a special case of first isomorphism theorem for vector spaces with one or two steps in between that I had too much trouble finding. If there's time at the end, I can come back and talk about it a bit more. So, okay, now that we've got that, we can start defining the relationship with subspaces and the orthogonal complement. So we're going to define a subspace as is it isotropic or coisotropic? We're going to say a subspace is isotropic if it's a subset of its complement. It's coisotropic if it's the other way around. It is Lagrangian, not Lagrangian. There we go, I got it the right way around this time. If the two subspaces are equal, and then it's symplectic if they are disjoint from each other, except for the zero vector. Okay, so at the moment, those are all just words. But using the rank, that was not as funny as I thought it would be. So using our rank theorem, we can now show that if we've got an isotropic subspace, the dimension of that subspace is less than n. And if it's co-isotropic, you can show that its dimension is greater than n. If it's Lagrangian, the subspace is equal to n, and then it's symplectic. That means the subspace has even dimension for any such thing. So the intuition that I sort of worked out for myself is if you've got a subspace U that is symplectic, that means it's made up of sorry, my brain is starting to implode. Okay. Okay, I know I'm going to put it into words now. Awesome. We don't need this anymore unless people still want to look at it. Everyone fine with not having R4 on the board? Okay. So let's say we've got a vector space V with basis E1, F1, E2, F2, and E3, F3. So the way you would get a symplectic subspace is that if the subspace for, I think that's the correct notation for subspaces, if your basis for your subspace B is just F1, F2, right? So now we've got even dimension, and if we find the orthogonal complement of this basis with respect to this one, we'll just be left with these vectors in the orthogonal complement. Okay? So that's, so a symplectic vector space sort of holds on to, if you're given a number, if a given integer I, you just hold on to all of the I basis vectors. So EI, FI together. But as soon as you start trying to mix EIs and FIs from, so like if you've got E1, F1, E2, but without the rest, you start getting the mixing with the isotropic and co-isotropic and so on and so forth. And then to sort of shed light on the interesting behavior we had in the examples I gave, where did I put it? I put the explanation in a different spot. Give me a sec. Yeah, so with the isotropic, we can guarantee that is true if we start with a subspace with dimension 1. So that means if you've got a subspace with only one generating vector, that means it will always be isotropic, which explains why the two examples I gave in R2 and R4 ended up being isotropic because we started with base 1. If I'd done a different example starting with two basis vectors for the subspace we're working off, we would have probably gotten a different result, specifically Lagrangian. So that's, I think I've spoken through everything I planned on saying. I think I'll call it the day here. I moved faster than I was planning. Sorry. Okay.